Hello, my name is Hamed, and I'll be presenting our work named Temporal System Call Specialization for Attack Surface Reduction. This is a joint work with my colleagues Tapti, Shachee, and our advisor Michalis, Polychronakis. Why do we need software debloating and specialization? Applications typically include code that they don't use and have access to features which they don't need. For example, some modules or plugins are not needed by a given configuration. Some library functions are not imported at all, and some system calls are never used. If we look at this simple code snippet, it only invokes two libc functions, strcopy and open, while when we look at the process address space, it has access to all of the library functions and all of the system calls. With software debloating, our goal is to identify the parts of the code which are required and remove the rest. So what's the security implication of this code bloat? First of all, the unneeded code provides more ROP gadgets for writing code reuse exploits. The unused system calls can be invoked in the exploit code to perform harmful operations, such as execve. Also, the unused system calls can be used as entry points for exploiting the kernel vulnerabilities that can lead to privilege escalation. The focus of our work is to reduce the attack surface by disabling system calls, both breaking the exploit payloads and neutralizing kernel vulnerabilities associated with those system calls. The existing work regarding library debloating lies on the fact that applications typically use only a fraction of the library functions. With library debloating, they remove the non-imported functions from memory by generating a call graph of imported shared libraries and identifying the library function dependencies. The caveat here is that the entire lifetime of the program is considered. So if a function or system call is used even only once, it can't be disabled. The question that we would like to answer is, can we disable more system calls by differentiating between a process's different phases of execution? Server applications typically perform initialization operations at the beginning of their execution. Operations such as reading the configuration file, forking worker processes, executing other programs, or creating files and setting their permissions. While when it transitions to what we call the serving phase, it starts performing the tasks which we actually expect from the program, such as handling client requests or establishing connections. If we look at the Apache web server as an example, when the program launches, the process address space has access to all of the system calls and all of the library functions. With library debloating, we identify these set of functions and system calls as unnecessary and unused, and we remove them. But there are still a set of security critical system calls, such as execve and bind, which cannot be filtered. If we look more in depth into the call graph, we can see these two separate phases of execution. And if we split the boundary, we can see that after the program finishes executing its initialization phase and it enters the serving phase, it doesn't require the security critical system calls anymore. And we can apply more restrictive filters and remove those system calls. With temporal system call specialization, we aim to disable additional system calls that are needed only during the initialization phase after the program enters the serving phase. We're able to disable 51% more security critical system calls, breaking 218 more shellcodes and raw payloads, and mitigating 13 more Linux kernel CVEs. As an example, Apache HTTPD and Nginx invoke execve only during initialization, while ID, bind, and Redis invoke chmode only during initialization. Now that we have a brief introduction, let's move on to how our approach and tool actually works. To give a top-level overview, we need the source code of the application and the libraries, and we compile them using LLVM with LTO optimization enabled. We require the programmer to specify the functions of the beginning of the serving phase. We feed the LLVM IR into SVF Anderson's analysis and generate our initial call graph. Due to imprecision, we apply two pruning techniques on top of that call graph, one type-based and the other address-taken-based pruning. When we acquire the set of required system calls, we generate seccomp filters to apply more restrictive filters. So our first step is to generate the call graph. We need a complete and sound call graph to identify the unnecessary system calls. Due to the extensive use of function pointers, especially in the programs that we have considered, we need to perform points to analysis. While sound, points to analysis comes with severe overapproximation. The overapproximation is to an extent which prevents us from differentiating between the different phases of execution and their system call requirements, leaving us with no security benefit. So our goal here is to improve the precision without losing soundness. Our first pruning-based technique is based on argument types. We match the arguments passed to the call side with the argument types of the function. We only consider struct types, no primitives and no void star, and we only consider non-varietic functions. If we look at an example from Apache, we have a call site which takes three arguments, int r, void star d, APR wait ts. SVF gives two target functions for this call site, pipe log maintenance and event run. Our technique works like this. We start from the arguments of the call site. The first argument is int r. It's a primitive. We consider it as a match. The next one is void star. We consider it as a match. The third one is a struct, APR wait t. So we start matching it with the target functions. For pipe-like maintenance, the third argument is also APR wait t, so it's a match. In the case of event run, the third argument is serve rec, and we can remove it from the target of this call site. Our next pruning technique is based on addresses taken. We identify where a function address is being taken, both global and local. We check if those locations are accessible from main. And then we prune edges to functions that are not accessed directly, and the location where the address is being taken is not accessible. Looking back at the example that we mentioned, the address of pipe log maintenance is only taken in start module, and start module is not accessible from main, so we can remove pipe log maintenance from the targets of this call site. Now that we have the call graph, how do we identify the required set of system calls for each phase? Applications typically invoke system calls to the standard C library. So we first generate a call graph for the glibc library, mapping all exported functions to their respective system calls. We do the same for all of the other libraries which the application depends upon. For these libraries, the leaves of the graph will either be other library functions or system calls. Then we generate the call graph for the application itself. And now that we have the complete call graph, we can specify any starting point in the program and see which system calls it requires. For example, if we consider main in this graph, we will see the set of required system calls. How do we filter these system calls after they have been identified? For this part, we use seccomp PPF, a mechanism implemented in the Linux kernel, which can be installed by invoking the seccomp or prctl system call. We install the more restrictive filters after entering the serving phase. Going back to the Apache example, the moment the program enters the child main function, we install the more restrictive filters and filter the security critical system calls. For our evaluation, we've considered 6 server applications. In this table, you can see the number of retained system calls and compare it between library debloating and temporal specialization. To give an example, let's focus on Apache. With library debloating, 105 system calls are required, while when we move to the serving phase of the temporal specialization, only 79 are required. So the 26 which are removed, let's look at how critical these system calls are. We'll do that in the next table. Looking at the security critical system calls, let's see which one can be removed with library debloating and which one can be removed after applying temporal specialization for each of the applications. Considering execve, for Nginx and Apache, it can't be removed with with library debloating, but can be removed after applying temporal specialization. If we consider chmode, setGID, or setuid, the same applies for lite, memcache, and redis. Library debloating cannot remove them, while temporal specialization can. In terms of the shellcodes and raw payloads, we collected 567 shellcodes and 17 raw payloads. We increased the set of shellcodes to 1726 by generating shellcode variations based on equivalent system calls. As an example, if you have one shellcode which has the except system call inside of it, we generate a variation and use except4 because the attacker could use except4 interchangeably instead of accept. In terms of shellcodes, we were able to break 20% more shellcodes compared to library debloating, and we were able to break 25% more raw payloads. In terms of Linux kernel CVEs, we were able to mitigate 13 more Linux kernel CVEs, which in some cases could lead to privilege escalation. To conclude my talk, temporal specialization removes security critical system calls by differentiating between the execution phases of a process. We proposed 2 novel call graph pruning techniques, and were able to filter 51% more security critical system calls than previous library debloating techniques, while mitigating 13 more Linux kernel CVEs compared to those techniques. Thank you for your attention, and I would be happy to take any questions you might have.